What questions do you have? Yeah, Marcus.
I got a question from you.
Okay.
It says a set of 3 vectors in R5 is necessarily linear independent.
Mm-hmm.
It was asking if the true or false and it's false. And it said the answer was a set of vectors 1, 0, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0 is linear independent in R5.
Yep. Why that's linearly
Yeah.
dependent? Okay, so remember that linearly independent means the only way that you can write the 0 vector as a linear combination is to use zeros for all your constants. Or another way to think about it is I can write at least one of the vectors as a linear combination of the others, right? So if I had the vectors, I think it was R5. Let's just look at those 2 vectors. Can I write one as a linear combination of the other? Can I do something to one of them to get the other? What do I need to do? Multiply by 2. So that means it has to be linearly dependent. Yeah. That's why it's linearly dependent. So I could add any other vector I wanted. I think I just used 1, 2, and 3 for the first components because that's clearly, they're all scalar multiples of each other. So they can't be linearly independent then. Again, the idea is that the vectors have to be giving you new information to be linearly independent. That's not giving me anything that is new, because anything that this vector generates, that one can. I just need to multiply that one by 2 times as much as that one. So it's not giving me any new information. That's the idea. It could, a set of 3 vectors could be linearly independent, but it doesn't have to be, is the idea. Other questions? And we're going to talk more about the linear independence and the span stuff here today, too. Okay. All right. Well, let's go look at this example that we started talking about right at the end of class last time. We had these other kind of well-known standard vector spaces where we talk about what the dimension is. Remember, again, the definition of dimension is the number of elements in a basis, because we know that if you have 2 bases for a vector space, they may not be the exact same sets at all. However, they do have to have the same number of elements in them, right? So Rn, we know from the standard basis for Rn, you can use 1, 0, 0, 0, 0, 0, 1, 0, 0, right? That's a standard basis. There's going to be n elements in there, so that has dimension n. What do we use for the standard basis for Pn? What is, let me ask again, what is Pn? What's that? It's polynomials, right? Degree n or less, right? So what's your standard basis for Pn? 1, x squared, all the way up to x to the n. How many elements are in there? N plus 1. That's why the dimension is n plus 1. M sub mn is n by n matrices. And so again, you'd have to put a 1 in each of the spots to get your standard basis. With zeros everywhere else, and so there's m times n elements in there. Looking at this example, we said that the dimension of the solution space here was 3. And let's talk a little bit about why. If I think about augmenting a vector of zeros here, creating that homogeneous system, right? We would notice that we've got, an x4, an x6, and an x7 as the 3 variables. Those are the ones that have no pivots in those columns, right? Agree? Okay. So we can write these solutions as your x1 would be a negative 3r, oops, sorry, not negative, be positive 3r minus s minus 5t. Your x2 would be negative 2r plus s, and there's no t there. Your x3 would be negative r plus 3s minus 2t. Your x4 is r. Your x5 would be negative 2s minus 6t. Your x6 would be s, and your x7 would be t. I know I did that quickly, but we've done those problems before, right? I have to move them over to the other side of the equation. That's why the signs are flipping. Notice we have three different parameters here, right? For the three different free variables. If we think about writing this in that parametric form again, I could write your general solution without having to write the variables over again. I'd have r times 3, -2, -1, 1, and then 0, 0, 0. You would have s times -1, 1, 3, 0, -2, 1, 0. And you would have t times -5, 0, -2, 0, -6, 0, 1. All right, just pulling off the r's, the s's, and the t's. I know I did it quickly. We've done this before. That's why I did that part quickly. That's not the interesting part that I want to talk about. I want to talk about dimension. Do you see a set of three vectors that can generate every single solution? Yeah. 1, 2, 3, right? I've got a set of three vectors that generates every single solution, don't I? Where did those three vectors come from? They came from the three free variables that we had, right? This one came from the fact that I've got a free variable that I'm using an r to represent the parameter, right? This one came from the free variable that I'm using an s. This one came from the free variable that I'm using a t. So I've certainly got three vectors that can generate all of the solutions, right? Okay. Why do I know these are linearly independent? Well, let's look at where those those parameters came from. There's x4, right? There's x6. There's x7. We agree? Okay. What do I notice that matches up? If I just kind of go across. What matches up with those ones in the other two vectors? Zeros, don't they? All right. Notice that this one here definitely gives me different information than those other two vectors, because this one can generate non-zero entries in the x4 spot. Can either of these generate non-zero entries in the x4 spot? No. This one gives me different information because I can get non-zero entries here in the x6 spot. Can I get non-zero entries in those spots? No, because there's zeros there, right? Likewise for that last one. Notice if I ignore the other four rows, what matrix do you see? The identity, which is exactly what we want to see if we want to see linear independence, isn't it, right? Okay. So that's why this has dimension 3. I've got three vectors that can generate all the solutions, and those three vectors are linearly independent. Okay. In general, when you're looking at the dimension of a solution space, the dimension of the solution space is going to match up with the number of three free variables that you have when you do the reduced row echelon form. Because each of those free variables gives you a parameter, which means that each of those is going to give you a vector that generates a solution. And they're all going to be linearly independent of each other. Okay. And you see this, and I know I use the examples a lot for differential equations, but you see this in differential equations a lot, right? When you do, if you've done anything with differential equations and solving, for example, if you haven't seen this, that's okay. But if you've got something like y double prime minus 2y prime minus 3y equals 0, I know that I can write the solutions here as a constant times e to the x and, no, sorry, it's e to the negative x, and another constant times e to the 3x. I know that from the form of the differential equation. The idea here is then what would the solution space be, do you think, for that particular differential equation? Not worrying about that, it's a differential equation. What do you think that the solution space dimension is? 2. I've got two different functions generating pieces, right? I cannot take a constant times e to the e to the negative x and give me e to the 3x. Remember, a constant times, right? That's the idea. I can't take a constant times this and give me that, and I can't take a constant times that to give me that. So they really are linearly independent of each other, right? And there's two of them. So the solution space has dimension 2. Now, it's a theorem in differential equations that I would know that to start with because of the fact that I'm doing a second order differential equation. I'm not worried about that. Okay. But I'm just trying to tie this back to the idea of these solution spaces. You deal with solution spaces in differential equations. You probably don't call them that, but you deal with them in differential equations. And the idea is that it takes that many different solutions to generate all of them. That's the idea of the dimension. What questions do you have on this one? Yeah. Not always. Our typical method is to put them in a matrix and row reduce, right? But this one I can just look and see that they have to be linearly independent by doing it that way. I didn't have to go through the row reduction. If you row reduce, you will see a pivot in each of the 3 columns. Because I could use this one to kill off everything there. It won't kill off anything else because of the 0 here. Okay, so you will end up with a pivot in every column. Yeah.
So when you say we end up with every solution, what solutions are we talking about? Homogeneous system?
The homogeneous system, right? We end up with all the solutions of the homogeneous system. Yes, yep. If it's not homogeneous, then it's not a subspace because the 0 vector is not in there. But we can write it as, and we talked about that before. We can write it as a particular solution and then plus the general solution to the homogeneous system. So this would be the part that would be the subspace. That gives you a shift off of the 0. Yeah, that's the idea. And the same thing would be true here if you do differential equations. If you've got something that's not a 0 here, the technique is to make it homogeneous, find that solution, and then do another technique to figure out what a particular solution is. Yeah. Other questions? All right. So one of the other topics, the last topic we'll talk about for new stuff today, and we'll do a couple more examples here as well, is the idea of playing around with sets and creating bases from a given set. So this is what's referred to as the plus-minus theorem. I'm not going to write out the proofs in all detail here, but we can see why it has to be true. Just going through a little bit of an argument. So the idea here is that if I start with a linearly independent set and I take another vector that's not in the span, so I cannot write that vector as a linear combination of the previous ones, if I throw that in, I still have a linearly independent set. And that makes sense if you think about that, give more information, right? So this set S is giving me some information, but there's not enough information here to give me that vector, right? So if I throw it in, it creates new information, right? That's the idea of linearly independent, right? Each vector tells me something different than any of the other vectors. That's the idea. It gives me more information, okay? This gives me a limited amount of information. This isn't in that information, so if I throw it in there, I get new information. So it's still linearly independent, okay? The idea is that, again, for linear independence, the definition is a linear combination that gives you the 0 vector, right? Okay. So let's say, just for argument's sake, that your S is, I'll call it W1 out to Wn, just so I have something to refer to. I start with a linear combination that gives me the 0 vector. Oops. Okay. So I'm thinking about taking a linear combination of all of the vectors in S and then plus the additional one I'm trying to throw in. Right? If this one is 0, say if your D is 0, then what do I have a linear combination of? I've got a linear combination of the vectors from S that gives me the 0 vector. What do we know about S? What are we assuming about S? Linearly independent. So what had to be true about all the C's? They'd have to be 0, right? So if D equals 0, then the C's all have to be equal to 0. Since S is linearly independent. Right? If the D is 0, then all the C's have to be, because we're assuming that S is linearly independent, right? If D is not 0, well, what am I allowed to do with a number that's not 0 that I'm not allowed to do with a number that is 0? Divide, right? So if D is not 0, I can solve for V, right? Oops. V would be equal to, I would move all of this over to the other side and then divide by the D. So you'd have negative C1 over D, W1, minus C2 over D, W2, all the way out to Cn over D, Wn. I could solve for V, right? What does that tell me? What have we written V as? A linear combination of the vectors from S, right? Can I do that? No. Because why? It's telling us that, bless you, by the way. What is it telling you? V is not in the span, right? Remember what the span is? The definition of span is set of all linear combinations, right? So this would tell me that V is in the span of S, which it's not, right? All right, so what has to happen? Can D be 0? Is D allowed to be 0? No. So D has to be 0. So we're back up into this case again, right? D has to be 0, which tells you that all the C's have to be 0. So how many ways can you write the 0 as a linear combination of all those vectors? Just one way, right? They have to use all zeros, correct? Okay. So that's what tells us that it's linearly independent, right? And it makes sense. Again, if you think about it as that information idea, I don't have enough information only using the vectors from S to give me V. I can't write V as a linear combination of the S's, the vectors from S, right? Right? So if I throw it in, it's adding new information. So it's still linearly independent. Okay. That's the plus part of the plus minus theorem. What's the minus part? The minus part is part B here. If V is in my set S, and I can write V as a linear combination, then do I need it? No, I don't need it anymore, right? So if I throw it out, that's what S minus the set V, that's set difference. It means throw the element out. If you're not familiar with the notation. This just says take your set S and take out the vector V. Okay. If I throw it out, I have the same information. I get the same set of linear combinations. Which makes sense, right? Yeah. Because if I take a linear combination that involves V, I just take the V out and put in the linear combination that has the other vectors of S in it. And I have the same answer. So that's the minus part. So the idea behind the plus minus theorem is that you can always expand a linearly independent set into a basis, and you can decrease a spanning set into a basis. So write that out. Any linearly independent set can be expanded to form a basis. And 2, any spanning set can be reduced to a basis. So if I start with any linearly independent set in a vector space, I can keep adding vectors to it until I make it a basis. If I start with a spanning set for a vector space, I can keep taking vectors out until I get to a basis. That's the application, the big application of the plus minus theorem. So let's talk about how that works. Let's look at these 2 examples, and I'm going to have a handout that says homework, but it's not really homework. I meant to give it out for homework, it didn't, and so we'll just use it for some more example problems. Okay, so I'll do that here in a second. But let's look at this first example. Without doing any work, you should be able to tell me, just by looking, that this set either cannot be linearly independent or it cannot span. Which one can it not do, just by looking at it? It can't span, right? The reason why is there's not enough vectors, right? How many vectors do you need? Minimally, how many vectors do you need to be able to span R4? 4, because the dimension's 4, right? I need 4 to be able to span. I only have 2, right? So without doing any work at all, that can't span. Okay? All right. So it is linearly independent for 2 vectors. Remember, to show that it's linearly independent, it's enough to see that one is not a scalar multiple of the other. What would I need to multiply 1 by to give me -3? -3. Does -3 times -4 give you 8? No, so they're not scalar multiples. Okay. All right. So it definitely is linearly independent. Here's how we are going to increase this set to be a basis. All right. So remember that our main trick to showing something is linearly independent, or show something is spanning, is to make a matrix, right? Okay. So in my first columns, I'm going to put the vectors in my set down the columns. Okay. And now I'm going to add vectors, not the vectors that I necessarily need. I'm going to add enough vectors to make sure that it does span. Okay. I'm going to create a spanning set, and then I'm going to take vectors that I don't need. Okay. How do I create a spanning set? Well, do you know a set that definitely spans Rn or R4? Do you know a set that definitely does? What works? The 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1, right? That definitely works, doesn't it? So I'm going to stick those in as my next set of my next columns here. Okay. Okay. Now that set definitely is not linearly independent, right? Okay. I want to use this to help me find a linearly independent set. Okay. What do you think I'm going to do with this matrix? Row reduce it. Yep. So do that. Now I can tell you for certain when you row reduce it, those first 2 columns will be that, without a doubt. How do I know that? What do I know about the first 2 vectors? Well, they know they're in far before. Well, what we know for a start, they're linearly independent, right? So I know that I'm definitely going to get pivots in those 2 columns, right? Okay. Anybody want to type that in and get a reduced row echelon form for me? Yeah, that I got to go switch to a different screen. I'm certainly not going to do it in my head. And I would not expect you to do it by hand, by the way. I expect you to be using your calculators to do this on the exam. Yes? Because it definitely does span, right? If I stick the standard basis on there, it's definitely going to span, without a doubt. Okay. So if I want to increase a linearly independent set into a basis, I'm going to just add the standard basis and I'll throw out the ones I don't need. That's what we're going to do.
That next column is -2, -1, 0, 0,
Okay.
and 0, 0, 1, 0,
Okay.
0, 0, 0, 1,
Okay.
-1, -1/3, -4/3, and 2/3.
Okay. All right. Cool. Thank you. All right. Which columns do you think matter for what we're trying to do?
3 and 6. Right? Those are the ones you're taking out.
Those are going to be the ones we're going to take out. Exactly right. Yeah. The 3 and the 6 are the ones that we don't want, because what does this tell me? This second column here, or excuse me, this third column here tells me if I do -2 times that vector and do -1 times that vector, I get that one. That's what this tells me. -2 times the first one minus 1 times the second one is going to give me the third one. So I don't need the third one. So I'm not going to use this one. All right? This last one tells me that if I do -1 times the first, -1/3 times the second, -4/3 times the fourth, and 2/3 times the fifth, I'll get the last one. Okay. It's the columns with pivots that matter. Okay? So I'm going to use, it's this one, this one, this one, and this one. But I want to go back to the original that corresponds. Okay? So my basis will be the 1, -4, 2, -3. The -3, 8, -4, 6. Don't use this vector. I want to use the corresponding one back in the original. I want to use 0, 1, 0, 0. And I want to use 0, 0, 1, 0. Those are the ones that give me new information. Okay? Let's think about it this way. If I just put in those 3 columns, and I said I wanted something times that plus something times that to give me this one, I get an inconsistent system because I have 0, 0, 1 on that side, right? So I can't write that column as a linear combination of those two. I get an inconsistent system, right? Because I'd have 0, 0, 1 if I think about my augmented matrix. Let's do a different one before we go to that last one. I want to look at part B of number 1 here on this sheet. Part A is just like this one. Okay, that's why I want to look at part B next. Too. All right, let's look at part B. Pardon me. I actually have this scanned in here. All right. First off, again, when I have a set of 2 vectors in a vector space, I can check that the set of 2 vectors is linearly independent by just noting that they are not scalar multiples of each other, right? Okay. So just like kind of like what I did with the vectors before, what would I need to multiply the 1 by to give me 5? 5. If I take 5 times the x, do I get 2x? No. So are they scalar multiples of each other? No. So the set's linearly independent. Okay. Does that make sense what I'm saying? Okay. For a set of 2 vectors, it's easy to check if it's linearly independent or not. Okay. Just see if they're scalar multiples. Okay. Well, what do I need to multiply 1 by to give me 5? 5. If I do 5 times x, do I get 2x? No. So they're not scalar multiples. Okay. I want to do this the same way what we did with the vectors. If I want to check, if you were using the matrix method to check this as linearly independent, I would use 1, 1, negative 1 down the first column, right? We agree? If I were going to use the matrix method to show that it's linearly independent, right? I put 1, 1, negative 1 down the first column. What's the second column going to be? 5, 2, negative 2, right? Okay. Now I want to do the same idea that we just did in the previous example. I want to add in vectors into this set that we for 100% certain know spans P2. What set can I add in that definitely spans P2? The 1, well, these are polynomials though. It's 1, x squared, right? So make sure you keep that in your mind because we're going to be adding these to this set when we're done, right? Okay. Now, in the matrix, what's it going to look like when I do that? 1, 0, 0, 0, 1, 0, 0, 0, 1, right? But remember, this corresponds to 1, this corresponds to x, this corresponds to x squared, right? Yes. Yes, correct. Yep, the dimension is 3, so I'm going to add the standard basis with 3 vectors in it. That's right. Yep. Okay. Now let's row reduce. I already know that I'm going to get 1, 0, 0, 0, 1, 0, 1, 0 here. Did you get it already, Austin? Okay.
Negative 2/3, 1/3, 0.
You're going down the column again?
Yeah.
Okay.
0, 0, 1. And then negative 5/3, 1/3, 1.
Okay. All right. So we added 3 vectors to start with, right? Really, we only needed to add how many? To get a basis, how many will we add? Just 1, right? And that makes sense, correct? Because it's P2, a basis has to have 3 elements in it. Which vector do we want to use then? 1x or x squared? X, because it's this column, right? That has the vector in it, or the pivot in it, I mean. So your basis for that one, I'll write it over here. Your basis will be the 1 plus x minus x squared, the 5 plus 2x minus 2x squared, and then just the x. Don't use 0, 1, 0, 0, 1 because that's not even a vector in P2, right? Vectors in P2 are polynomials. I want to make sure I use the polynomial that corresponds to that. Also, don't say it's x squared because it's in the third column and in the third row, right? It's not this specific column that matters. It's I have a pivot in this column. I'm going to go back to the original matrix's column and use that information. I'm trying to figure out which of these 3 things I needed to add, right? When I do the reduced row echelon form, it says I needed to add the second one. So I needed to add the x. Thinking about it another way, I can get 1, just the constant 1 from those 2 things. I can also get the x squared by itself just from those 2 things, but I can't get a single x by itself using those 2 things. Does this idea of adding vectors to create a basis make sense? Okay. Reducing it to a basis is even easier because I don't need to add things to it. I'm trying to throw things out, okay? So let's look at this number 2, and then we'll go back to the other example that's on the handout. How many vectors are in that set? 4. Where do these vectors live? What space do they live in? R3, right? We agree? So how do I know that this set cannot possibly be linearly independent without doing any work? What's the largest linearly independent set you could possibly have in R3? 3 elements in it, right? Once it gets past 3, it's too big to be linearly independent, right? The dimension gives you the largest possible linearly independent set and the smallest possible spanning set. Okay? It's too big to be linearly independent. The dimension is 4. I can't go any higher. Excuse me. The dimension is 3. I can't go to 4 and keep it linearly independent. Okay? I don't need to do any work for that. Literally, dimension is 3. Size of the set is 4. It's too big to be linearly independent. Okay? All right. Is to show that it spans. How do you show something spans again? What do you need to do? Pivot in every row when you make your matrix and do the reduced row echelon form, right? So make your matrix. I know I didn't leave myself a lot of room on this sheet. Make your matrix. It says show that it does span. So I know I'm going to get a pivot in every row. So you better see a pivot in every row if it's going to span, right? So what do you get for your reduced row echelon form?
Coming down the columns, 1, 0, 0, 0, 1, 0, 5, negative 1, 0.
0, 0, 1, good. So the fact that you've got a pivot in every row, that's what tells you it spans, right? Remember again, linearly independent is pivot in every column. Spanning is pivot in every row. Okay, so that's what shows that it spans. Now looking at the reduced row echelon form, which vector did, or which column did we not need? Which vector do we not need? The third one, right? This is the one that doesn't have a pivot in it, right? That's the column that doesn't have a pivot, so I did not need that vector in my basis. So your basis would be the set of with the other 3 in it. Notice that's exactly what we did here, isn't it? It's exactly the same process we did here, isn't it? I had a set of vectors that definitely spanned, but I didn't need this one or this one, so we threw them out. It's the same process. Okay. All right. So let's go back over to the handout. Yes. Correct. Yeah, there'll be the 3 columns that we needed, not the one that we didn't have the pivot in it. Yep. Okay. Oops.
Question about this thing. Why aren't we doing the 0, 0, 1, 0, and 0, 0, 0, 1? Why aren't we using those 2?
For this one, this example? So why are we using
The 4th and 5th.
here?
Yeah.
Okay, so remember, it's not these vectors. These are the vectors that end up with pivots, right? Okay, we want to go back to the original columns that they correspond to grab the vectors. Okay, so I grabbed that one and that one. That's why I put those in. Yeah. Okay. And again, the reason for that is if I ignore everything else and I had only put in column 1, column 2, and column 4 and row reduced, I would have got an inconsistent system. What that tells me is I can't do something times that plus something times that to give me that one. So that's why I want to make sure I keep that one. That's the one I'm going to throw in. Okay. All right, let's look at the next one here. What's your dimension of P2? P2 has dimension 3, right? So one more, because you have to have a constant, an x and an x squared. There's 3 pieces of information, right? How many vectors are in this set? 5. So which do I know automatically cannot be true? It cannot be linearly independent or it cannot span. It cannot be linearly independent. It's too big, right? The biggest linearly independent set I can have in P2 is 3 elements, so this is too big. Do I know for a fact, though, that it spans necessarily? No, I have to check that, right? I don't have to check that it is linearly independent or not because I know it can't be. It's too big. But just because it's big enough doesn't guarantee that it actually spans. I have to check that part. Okay. How do I check that it spans? What do? Make a matrix and row reduce, right? So our first column will be 3, 1, negative 1. The next one will be 2, 0, 3, 1, 3, negative 15, 0, 1, 2, 0, negative 3, 9. Yes?
There's always more rows more columns than rows. And we always say that it's not going to be linear.
Correct. If there's more columns than rows, yep, that's exactly right. And vice versa for spanning. Yep, that's exactly right. Yep. Also, did you already get it? Okay.
1 0 0 0 1 0 3 negative 4 0 0 0 1 negative 2 3 negative 1.
So which of the original set do you want to keep? Yeah, the first, the second, and the fourth. Yeah, definitely.
Is it just a coincidence that every time it's been the third and the last?
It is just it's just a coincidence. Yes.
So weird.
It's just a coincidence. It's because I'm an original one. I make up problems. That's part of the problem. I didn't always want it to just be the first one, so I try to make, but then I don't. It didn't make one like be the last one or just the first one. So yeah, it's just a coincidence. Yeah. Okay. That one okay? Let's go shift back over to that homework problem again, or that homework sheet again. And I want to look at, I want to look at this number 5. Because it also lets us review a little bit. How would I show that it's a subspace? I'm not going to go through the proof of the subspace, but how would you show that it's a subspace? What do you need to check? Close under addition and scalar multiplication, right? So I need to make sure that if I have vectors in there, I can show that it's closed under scalar multiplication, closed under addition. Just looking at the subspace, notice the problem is asking you to calculate the dimension, right, of the subspace. Well, what would be the biggest it could possibly be? Without even thinking about it, what's the biggest the dimension could possibly be? 5, because where do all these vectors live? In R5, right? Okay. Now, it's probably not going to be all the way up to 5, just because otherwise, why would I ask the question, right? Okay. What do you think it is? What do you think the dimension is? Just by looking at the problem, what do you think the dimension is? No, we're not worrying about the vectors. Just look how the subspace is defined. What do you think the dimension is? So 1's a good guess, right? Why are you thinking 1? Okay, so as you add up add up to these different things, I have to get a 0, right? But let's think about it from a different perspective. If I choose whatever I want for x1, think about it that way, I could still choose whatever I want for x2. I haven't got a problem yet. I could do the same thing for x3. I could do the same thing for x4, but once I've chosen those 4, do I have any choice for x5? No. So how many choices do you really have? 4. So what do you think the dimension might be? 4, right? Also, you can think about it from a reduced row echelon form idea. I've got a system of one equation with 5 unknowns, right? I could write my matrix as this, couldn't I? My augmented matrix this way. Do I need to do anything to do reduced row echelon form? No, it's done. How many free variables do you see? 4, right? I've got 4 pivotless columns here. So it does have dimension 4, okay? Yeah. Say it again. I do care about x5, but I don't have any choice. If I pick x1, x2, x3, and x4, I know what x5 has to be to make it equal to 0. I don't have a choice for what the x5 is. That's the idea. Okay. So I'm suspecting that this has dimension 4, right? Okay. So if I want to check, this problem's asking you to figure out which ones make a basis of these 8. What do you think we're going to do? Make a matrix and row reduce, right? Okay. So I would have my first column would be 2, -3, 4, -5, and 2. I've got a second column. I've got a third column. Lots of columns here. By the way, I would not on the exam make you type in this is going to end up being a 5 by 8 matrix. That's a lot of things to type in without making any mistakes. Austin's working away at it. Bless you. Yeah. Say it again. Well, we'll see when we do the reduced row echelon form here. Do we have it? Anybody have it? I know Austin's still typing. I can tell you what the last row is going to be. It's going to be a row of zeros. Yeah, it should be a row of zeros at the end. Okay. I don't know if I have. Oops. Yeah, of course it went off. There we go. Let's see, do I have this installed or I can do this quickly? I do. Oh, for heaven's sake. Really? Oh, jeez. Fine, I can't do it that way. I was just going to try to type in real quick. Did you figure out where it was? Aha. That's why I said I'm not going to make you type in a 4 by 8. Okay. Why is it not on there? Come on. Let's get back on the screen. There it goes. Well, theoretically it went. Oh, it bumped them. There we go. All right. You gonna go down the columns again? Okay.
1.
Okay.
-3, all zeros. 0, 1, 0, 0. 4, -2, 0, 0. 0, 0, 1, 0. 1, -2, -4, 0. 0, 0, 0, 1. And then -1, 1, -2, -1.
Okay. So which are the columns that you want?
1 and 1, 5, and 7.
And third one? Yep. All right. So you want columns 1, 3, 5, and 7? Because those are the ones with the pivots, right? So we would use V1. Your bases would be V1, V3, V5, and V7. And notice I really do have dimension 4 there, right? Because there's 4 elements in the bases. Yeah. Okay. I didn't write out what the vectors were, but that would be what they are in this case. And then just one little quick review, just to make sure that we're all on the same page. Notice the last part says, find the coordinates, or expresses a linear combination that's also find the coordinates with respect to the bases. How would I do that? Augment it with the 4 vectors that we just came up with, right? So you would take your 2, 3, 4, -5, 2, your -6, 9, -12, 15, -6. Your, oops, that's not the right one. That's not column 3. 3, -2, 7, -9, 1. -1, 1, 2, 1, -3. And 1, 0, -2, 3, -2. And augment it with the 17, -82, -46, 3, and 108. And row reduce.
And the reason why we didn't add the identity matrix to the first, we didn't augment the first matrix with the identity matrix because we had the right dimensions.
We weren't trying, so we augmented the identity matrix before because we were trying to expand a linearly independent set. This is the other way around. We're reducing.
Oh.
Yeah, we're reducing down. So, yeah. All right. So anyway, once you get the answers there, you should have 4 answers when you're done. I know I'm out of time. Did you happen to get the numbers, Austin? Ooh, that shouldn't have happened. Oh, I can finish it. I know where. It's okay. I'll get the answers to you. Once you're done, you should have 4 answers. So there will be 4 coordinates. The reason why there's 4 coordinates is because we have 4 vectors in our bases. All right. In any event, this is how we increase bases, or sets to bases, and decrease to form of bases.